I think so. Can I go? Yes. Okay, so I will, this talk is about neural network applied to the selection of trigger in a period of where only one detector operates. So I start usually this talk with the introduction, even if probably for you is for this audience is not necessary, but okay, since it's here. So in this plot you see an example of our typical gravitational wave signal. So the strain as function of time with the typical spiral merger and written down phases. But as you know, when we look for this kind of signal in the data, we realize that they are not easy to find. They are really hidden in the data. And then these signals are rare, weak, and the background is really complex. It's not Gaussian, it's not stationary. This is, I don't remember which RAM is, probably O2. A typical example of the noise as function of the frequency. So we usually operate in the bucket around 100 Hertz, and below 10, 20 Hertz and above 1000 Hertz, we are a bit dominated by the noise. Then, as you all know, besides the stationary, the noise that is always there, there are the glitches. There are many kinds of these transient noise, and they can really mimic the background. We have had many talk about that, so about the beep, the whistle, and so on. When machine learning is applied to signal detection, to gravitational wave signal detection, the first decision you have to take is about data representation. And usually the two choices are images, so 2D spectrograms, or the time series as it is. And there are some reasons to prefer one against the other, but okay, we decided to go for time series. So what I will then the network I will show use the data in the representation of time series. And in this regard, there are many papers that are done trying to do something similar, but usually many of these papers, even if they start, because it's normal to start with one detector data, the goal is usually to put together data of many detectors to reduce the false alarm rate. And instead, what we want to do here is try to solve the problem in the case when only one detector operates. Because in this case, the impact of the glitch on the sensitivity is large, because the coincidence that usually is used to remove the background is impossible. So this work started with this question: can machine learning help in this specific case? And I checked a bit the amount of time in which, 1 or 2 or 3, the detector were operating in as single detector, so without partner. And this is not a negligible amount of time, so almost 3 months in O1 plus O2 and a bit more than 1 month in O3. So focus on this period could be useful. And even if it's true that in general, for the next operation, for the next observing run, we we always try to have coincidence time. It's not obvious that we will always be able to do that. So we decided to also, instead of using the typical approach of noise against signal, we decided to use 3 classes in our classification. And the data that we have used come from gw1, because when we started, that was the only one available. And it's downsampled to kilohertz and then watt. And so the 3 classes, as you can guess, are the noise, so pieces of real detector noise where we know that there are no glitch, no signal, no injection, and these are open data where we know the status of the detector was good. And then the signal is obtained basically taking the same data in the same condition of the noise and injecting signal, so a BBH basically. I will say a few words about that later. And then the 3rd class are the glitch. So using gravity spy, the coherent wave bus, we can infer the position of the glitch, of course, in more than 2 detector periods. And that is used as other training and testing class. Okay, so these are other details. So the segment, the duration of the segment is fixed at 1 second. We actually, at the beginning, we played with different possible lengths, and then we decided to focus on this. There is a bandpass filter. At the moment, it's like we took 1 month of data and we took all the 1 second segment in this 1 month of data without superposition. And the position of the glitch is random in the segment and also the position of the signal. These are the numbers of noise signal and so on. And the BBH have been like they have all parameters random, and the masses are chosen in the interval between the sum of the total masses between 33 and 60, and the SNR between 8 and 20. And the choice of the masses you can easily guess. It's to be sure that the signal are included in this 1 second segment, that are completely included in this 1 second segment that we are using. So we started to work on this with the idea of finding the smallest CNN that would solve our problem. Let's say we would classify the 3 classes in the best way. And these are all the parameters. So it's a small network. It's very similar to other papers of the same topic. So the 4 convolutional layer and 1 fully connected layer. And then, as you know, you get in output the probability of belonging to each of the 3 classes. Then you can print, you can plot one of these probability. For example, this is for each class, the probability to be classified as signal, and you can use this probability as threshold to say everything that is above I consider as signal, everything that is below this threshold I consider as background. And even if, so one thing, it's true that we decided to separate glitch and noise in training, but then in the result that I will show, we put glitch and noise together. And what I will show is always signal against glitch plus noise. So this is a typical plot of the efficiency as function of this. So this is the same probability here, and this is the efficiency. And the colors refer to different thresholds in SNR. As you can expect, when you put a higher lower threshold in SNR, these basically are all data. So SNR greater than 8, that's the efficiency you get. And then when you increase the SNR, you increase also the efficiency. And of course, this then has to be coupled with the false alarm rate. And this is an example of the fraction of noise classified as signal. And here noise and glitch are separated. The noise is always in green, the glitch are always in red. And here you see the comparison between some different architecture. So the circle, so the one in the middle, basically, is what we refer as standard configuration, so the one that we use as a reference, let's say. Then the square that are here are basically obtained changing the optimizer, so using NADAM instead of NADAM. And then with more filters in the same architecture, we get this triangle. And of course, what you need is put together the efficiency and the false alarm rate with the ROC curve. And this is an example with the two different thresholds in SNR. This is SNR 8, this is 14. And the performances are quite similar. It seems that NADAM helps a bit. And of course, with this more filter, also the training time is much longer. Then when we arrive at this point, we start to evaluate different possible architecture. So, because in the literature there are some architecture that are specifically meant for time series, and I will show two results. One that is called the temporal convolutional network, and one that is called inception time. Then recently there was this the Hubble competition, and a lot of results used this efficient net. We have not implemented that, but maybe this would also be one possibility to try. So this TCN is very easy to install. There is this paper that describe it. At the end, you basically are. And the idea is that they use this casual convolution. So the convolution happens also only back in time. And so you can find in all the details in the paper. And the result, we have the 32 filter and the kernel size of 16. I tried a bit of combination, and this seems to be the best one, paying attention that the receptive field was more or less of the size of the time series. The other architecture that is called inception time, I think I put a reference somewhere. Okay, sorry, I put a reference here. Basically, in this case, the idea is that you slide a convolution with different number of filters back and forth in the same time series, and then put everything together, basically. And so these are some results. Basically, these are the same plot that I was having before, but with the addition of this gray curve here, that is the temporal convolution network. So you can see that there is a good improvement. But it seems that you can't reach false alarm rate, false alarm probability less than 10 to minus 3, 10 to minus 4. I tried to convert this number in number of false alarm per month using the amount of noise segment and glitch segment I have in this specific 1 month of or one. I think this is not sure it's a good estimate, but as you can see, it's something around 100, 1,000 false alarm per month, year. So it's still too high. And then we realized that there was like a bit of the problem we were experiencing, the problem, probably some effect of the softmax activation, probably some similar effect to the one that Andre was talking a few days ago. And then what we did was, instead of using directly the standard way after the softmax, we calculated from logic, so from the output of the network without the normalization. And this makes a good improvement. So basically, the orange line would be the standard thing with the softmax, and the blue line would be the one without it. And okay, here the legend is in an inconvenient position, but you see that the last point here is between 10 to the 5 and 10 to the 4th, and here you arrive almost at the limit of the statistic that we have, so almost 10 to the 6. And then, so this result was specifically for the for ET, for inception time, and but with the TCN, so with the other specific network, we get very similar results. And this is calculated after the final softmax. This is before it, but in any case, it's more or less the same. So it seems that it works, and we are basically at the limit of the statistic that we are getting now, and we have tried to use a special architecture specialized for time series, and it seems to work. And now we're thinking if we can work on there are alternative loss function in which you try to optimize the CNN with some specific objective instead of the standard accuracy, categorical cross entropy, and so on. So that's what we are working on at the moment. And okay, the work is in progress, but I hope we decide at some point to stop and write a paper about it, because it's years that are going.
Didn't you already decided?
Yes, we already decided. Okay, that's it.
Thank you very much. Questions or comments?
One of the most difficult things in machine learning talks is for me always all the vocabulary people use for positives and negatives and so on. And you had one plot that I didn't quite understand. I think it said efficiency against signal recovery or something like that. It was quite early. Oh, yeah. This one.
So here the point is that, so you see, this is one of the 3 numbers you get, no?
Yes.
And the idea is that with different cut, so this was to check which efficiency we get with cutting on this probability. So,
so if you cut x-axis is the threshold.
Yes,
okay,
yes, yes.
The midpoint is the same positive.
Yes.
Okay, that makes sense. If I may, 1 or 2 earlier, no, 1 earlier, this one. This one looks super impressive. You basically have exactly the same behavior on noise and population.
Yeah.
So based on that, you should really blow mesh filtering away, shouldn't you?
I don't know.
Because normally the Gaussian noise distribution falls off very quickly, and then all the tail that makes things difficult are the glitches. I think that looks really promising.
Yeah, hopefully. So because then we tried also to put together noise and glitch, but with 3 classes it seemed to work better. Even if, I mean, at the end we have to put together the glitch and the noise, but yes. I've done dozens of plots like this with different output of different, it's always more or less like this. I don't know.
I think it was not really by design, it just
no, exactly.
Like that, right? We were focusing on detecting signals rather than discriminating between signals and non signals. Other questions?
Could you please go back to the slide almost at the end where you mentioned seeing a similar effect as we did? Yeah. So could you explain to me, please, what exactly is recall?
The true positive rate. So efficient, I don't know, it is, yes, we had a student that decided to use that. I don't know.
Our issue was that as we moved the threshold and we moved along the curve, we got to a point where the threshold was 1.
Mhm.
And so in one spot at a certain false positive rate, the network just jumped to zero sensitivity.
Mhm.
I'm not
No.
sure I understand the connection.
No, the connection is just that I thought that, so as you can see, so I thought that what you observe is some induced to some rounding that the softmax does. And here, without using the softmax activation during the traction, during the training, it seems that the results are improved. So maybe this rounding has some side effect also on that. It's not exactly the same. Yes, that's true. I understand what you mean. Yeah, the activation. Yeah.
Okay, yeah, I understand similarities now. Am I allowed another question? Could you also elaborate a little bit on what exactly the inception time is?
So, so I read this paper time ago, so I'm not really able to explain it in detail. But as far as I understood, the idea is to combine kernel of different size, like at the same time, and sliding them, and then putting all the result together. I think that the main idea was this, if I understood correctly. And so if you check this paper, where is it? This one, they compare it with different other kind of networks on time series classification, and they show that this inception time works better. Of course, everyone says it is works better, but
Okay, thank you.
you're welcome.
Yeah.
Thank you, Gata. Nice talk. So you measure performances only through recall. Like, I'm always confused. This is true positive, right?
So yes, I'm
And
sorry.
how about another three combinations? False negative, true negative, and false. This is you need
So basically, I'm sorry, but
false negative.
exactly. So in
True negative, sorry. True negative. This is precision, right?
yeah, I don't know. We use the standard ROC code. I'm sorry if the name of the axis is different, but they always mean true positive rate and false positive rate, basically. So classification efficiency and false alarm probability. I don't know. These were the usually are what we in general refer now. I don't know what you would suggest that.
If you say measure just recall, and if you classify everything as positive, your recall will be 100%, right?
Mm-hmm.
So you need another measure which will help you to distinguish between false positive.
And which is the false alarm probability.
Usually,
yes, usually the plot are like the efficiency on the y-axis and the false
you
alarm.
call it efficiency. Okay.
Yes, I don't know. Sorry, you are right. There are a bit of complication here in names, but this is always the true positive rate on the y-axis, and on the x-axis the false positive rate.
Okay. Thank you.
David has a comment, so I will come back to you.
Just wanted to add something maybe to discuss about how people see people coming from the applied side who are very interested in false in true negatives. So there's also the standard measure accuracy, which is true positive plus true negative. But as a gravitational wave person, so far I've never cared about that, and I've never seen an argument why that would be interesting for our case. I don't really care for the noise. So if anyone has an argument for it, I'd love to hear that over coffee.
We can come back to you around.
Hi, thank you for the talk. It's not really a question, but more to have your opinion. From all those architecture, which one do you think is performing best, and do you think it's more promising for the future?
So, I don't know, these two, they both seem to work quite well. There are still things that I don't fully understand in the sense that, so with this inception time, you are not really able to train for many epochs because it starts to overfit. So these are really few, like 10 epochs. I cannot, I'm not able to train it more than that without overfitting. So this is a bit worrying. The TCN instead needs a bit more of epoch to be trained, and it doesn't overfit as quickly as the inception time. I don't know. They have similar results, so probably it's the same thing.
Yeah, I think it's really a benefit to use those kind of techniques.
Yeah, because so this is sorry, I should have put as you can see from the graphic, it's part of the code difference, so that's why I didn't put all together. But you see, so this should be comparable to what you see before, and you see that this TCN is you got a good improvement both in efficiency and false positive rate, and then this is even better than the plot before, because so I think there is a good improvement.
Okay, thank you. That's very nice.
I myself am quite a fan of this temporal CNN because it's like a CNN, so you can fairly quickly train it, and more or less there's nothing really magic in it.
It takes
it takes more
longer.
time, of course, right? But it's kind of on the conceptual level.
Yeah, from the conceptual, yes.
Yeah, so my question is, for the inception time, is like the model is already available and
Yes,
loaded?
yes.
Okay, so.
So that's why I don't know the details.
So you don't tune any other parameter, it's just like.
The minimal standard of
Just,
things,
okay.
the standard things, the number of fits, how many times. So, but there is, so if you, if you go to this reference, they have, you know, the typical Git repository together. I don't remember if I pp installed it or I just copied. I don't remember, but I think it was very, very easy to include in our project. Very easy to implement.
And so if I'm just quickly to the minimal, it's possible.
As I said, it's a bit slow, and you are not
Okay,
able
so
to.
it's slow. Okay.
It's slower than the typical CNN. Like I don't like it takes 1 day for really few epochs, so it's a bit slower.
Okay, thank you. Thanks. Other questions? Just my comment at the end, our question to everybody. Did anybody of us actually use efficient net in our applications?
I think there was one talk a few days ago. Someone, I don't remember who was.
Okay, sorry. Okay, because this is what I mean, that's development. Okay, thank you, Agata. And so, and I invite the second speaker. So we have to.
It's very important.
Okay, we download it.
enter in the buttons.
Thanks.
And this is already sharing, right? Okay.
So the second talk is about modeling compact binary waveforms.
Can you hear me well? Excellent. Okay. Perfect. So I'm Maite Mateo. I'm from the University of the Balearic Islands, and I'm a third-year PhD student. So I'm going to explain you a bit our ongoing project on modeling compact binary waveforms using machine learning techniques. So first of all, let me talk a bit about waveform models themselves. So in order to really identify the nature of the source of gravitational wave events and infer their parameters as masses, spins, and so on, we really need very accurate waveform models. And these waveform models are built using information from numerical relativity, but also perturbative results, such as the post-Newtonian theory and other approximations. There are currently three main families of these waveform models. First of all, we have the surrogate ones. We just interpolate waveform numerical relativity simulations. And they are very accurate because they are calibrated to NR, but as you know, they have a lot of limitations in the parameter space because numerical relativity simulations are really expensive. Secondly, we have the effective black-body family, which model the Hamiltonian and the radiative flux integrating ODEs. And this procedure, in terms of evaluation of the model, is very costly. Finally, we have the phenomenological waveform models, which are the ones that I'm going to talk about in this talk, which are simple and fast because they are built using piecewise closed form expressions. So at the moment, they are not a generic waveform model that includes both the precession treatment and also eccentricity. At the moment, we have aligned spin models, which assume quadricircular orbits, which are calibrated to numerical relativity simulations. And then we also have the precessing ones, which also assume quadricircular orbits, and their numerical relativity simulation calibration is quite limited yet. So just a quick overview about the current status of phenomenological waveform models. During the 01 period, there were the third generation phenomenological waveform models, which were simple and accurate enough for the sensitivity of the detectors at that time. But however, for all three, we were needed much accurate waveforms. And here becomes the importance of the fourth generation phenomenological waveform models, which includes much more accuracy, adding also higher modes, mid frequency for precession, and speeding up algorithms. The most important is IMR phenom XPHM, which is built in the frequency domain, but we also have the time domain family, which is IMR phenom T, which brings all the techniques for building phenomenological waveform models from the frequency to the time domain, adding also some improvements in the treatment of precession for high masses. So, as you know, waveforms can be modeled as a sum of spherical harmonics, being the two modes the dominant one, and for the merger ring down, the subdominant ones became more important. So in order to model these spherical harmonics, we in the phenomenological waveform models, what is done is the following. So we split into the phase and into the phase and into the amplitude, and these two quantities are split in three different regimes: the spiral, the intermediate, and the ring down. And we propose these piecewise closed form expressions. So we guess an answer for each of these six regimes, in fact, described by some coefficients, and these coefficients has to be fitted across the parameter space. So let's explain this a bit more in detail. So as I said before, we propose waveform ansatz for the 6 different regimes, combining knowledgement about post-Newtonian theory, black hole perturbation theory, and also numerical relativity. And we also give insights of analytical solutions, for example, for the stream accelerator regime, and also numerical studies of calibration. So at the end, we have few coefficients of these answers that, the parameter space will be described with this few number of coefficients that we have to fit. So in order to do this fit, first of all, we have to do a direct fit in order to find which are the most convenient coefficients using a calibration data set. Secondly, once we have this fit, we have to do a parameter fit across the whole parameter space. So, which are the dependency of these coefficients across the whole parameter space. And once we have all this information, we join them together and we have the phenomenological waveform model built. So here you have an example of which were the ansatz proposed for the IMR phenom XPHM, which is the line version of the XPHM that I was talking about before. So basically, as you can see, we have 2 proposals, one for the phase and one for the amplitude for the inspiral, intermediate, and bring down. And there are these coefficients that are the ones that has to be fitted across the parameter space. So in the aligned spin case, these fits have been done using numerical relativity simulations. However, for the processing case, this is more difficult. In fact, in order to, well, it's more difficult because in the processing case, we have a much more high dimensionality, and it's more challenging to fit to numerical relativity. So in order to skip this calibration to NR, is used the twisting up approximation. So they identify a co-processing waveform with a non-processing one. So at the end, we do the rotation into the co-processing frame using the Euler angles or the quaternion description. And this is what is employed currently. However, in order to have more accuracy in the processing waveforms, we need really to try to calibrate them to numerical relativity. And this is what our current work is about. So as I said to you, in the processing case, the dimensionality is much higher. So it's very challenging to fit to numerical relativity. So using machine learning techniques will facilitate us this procedure. So in this work, which is in the very beginning, we try to predict the random quantities of a binary black hole using machine learning. So in order to train this model, we use numerical relativity simulations from the SXS catalog, which are about 2,000 binary black hole simulations. Using, well, we split them in 2. First, the aligned spin case, and secondly, the processing one. And as you can see, the number of examples is very small. So for the aligned spin, we have 593, and for the processing one, 1,423. So in this catalog, there are information about the time evolution for the orbits, the waveform, and spins. So we pick all this information in order to build our data set, and we will try to predict the final spin of the binary black holes and the radiated energy. We use the LAL for creating this data set. We follow the LAL convention. So let's now discuss a bit what's the aligned spin case and the processing case for the ones that don't know. So in the aligned spin case, as you can see here in this picture, we have that the individual spins are aligned or anti-aligned to the orbital angular momentum and perpendicular to the orbital plane. So that means that during the evolving of the spins, their directions is not changing with are not changing with time, and the orbital plane is also preserved. So this is a quite simple case, and can be fully described with 3 parameters, which are given by the 2 Z components of the spins, and then the mass ratio, either the symmetric or the asymmetric. In order to build our data set, we follow the intuition given by the Positonian theory and also some studies using numerical relativity calibrated models. And we decide not to create our data set giving the Z components of the spins, but the relation between them. So the difference between them, and also the chi effective, which is the average spin perpendicular to the orbital plane. So here you have a correlation matrix. I don't know if you can see very well the values, but just to say that these coefficients that we are going to use to train our model are strongly correlated to the output that we want to predict, which is the final spin and the radiated energy. So basically, we decided to train a regression model using a deep neural network, a very simple one, because the amount of data that we have to train is very small. So in order to reduce overfitting, we also use dropout, and the results are quite good. So we have both for the radiated energy and for the final spin, very high accuracy. And in order to really understand our results, we decided to compare to current models that exist. So first of all, we compare it to the NR surrogate, which, as I told you before, the coverage range is reduced, so it's up to Q8, and it spins it of up to 0.8. And also we compare with IMR, the approximation used for IMR phenomena and SUOB. So in order to really understand our results, in the line spin case, we decided to create some subsets in order to reduce the dimensionality of our data and really understand our results. So first of all, we collect all the data for the equal mass, equal spin. So I don't know if you can appreciate very well the colors, but the red one is our deep neural network, and the black dots is the NR simulation that we have to train the model, and the other curves are the current models that we are comparing them. So as you can see, in this case, this is the plot for the final spin, and it is for the radiated energy against the chi effective, which is the only dependence in this one-dimension set. So you can see that here, when the range of the interpolation is really high, because the points that we have for numerical relativity are really distant, we are not super accurate, both in both predictions. We also see here in the subset of non-spinning, where the only dependence is in the mass ratio, that here we only have information of NR simulations for big symmetric mass ratio. So for the extreme mass ratio, we don't have enough information. So as you can see here, for the chi effective, we have kind of good results, but not super good. But for the radiated energy, we have very bad results in extrapolation, because as you can see here, in fact, we are predicting negative information. So how can we solve this? So this is the extreme mass ratio regime, and luckily we have analytical results for this extreme mass ratio. So we will add analytical knowledge in our dataset in order to solve this problem. So and finally, for the equal spin data, which is a two-dimensional set depending on the mass ratio and chi effective, we see exactly the same behavior as here. So for extreme mass ratio, we have negative radiated energy. So what about these analytical results of extreme mass ratio regime? So basically, in that case, we have a test particle orbiting a Kerr black hole. So the small black hole blanches when it reaches the ISCO, and in linear order of the asymmetric mass ratio, we have that the radiated energy is equal to the energy of the ISCO. So basically, the final mass is 1 minus the ISCO. So the energy and orbital momentum are given by these formulas, and we can numerically solve this equation in order to get the final spin. So we have the solutions for these stream mass ratios. Just to take into account that the final spin has to be, the final black hole has to be a Kerr black hole, and that the derivative has to, in that regime, has to be decreasing monotonically. So these are super preliminary results. In fact, they are results from the last week. So we have to tune the model and study the case much more. But these are just to show you how results are changing, just adding this extra data. So these red points are the ones that are added from the stream mass ratio. We added 300 points of this analytical solution. So for the non-spinning case, that, as you can see here, the orange one is the one without embryo data, and the green one is with. The behavior is changing a lot. So we have to really study more how does it depend on how many points that we are adding to the data, and also how to change really the deep neural network to really fit correctly these quantities. As you can see here, also for the equal mass spin, we are fitting much better these points of large interpolation. However, we are losing information here for large chi-effective. And finally, for the two-dimensional subset, the equal spin, this slope that we had for extreme mass ratio has disappeared as well. Another regime that has to be also studied in order to cover the whole parameter space is the aligned spin case, which is very challenging because we don't have numerical relativity data here. A thing to have to take into account is that different ansatz proposed by different models produce several discrepancies. So for IMR phenom X, it assumes that the final black hole is a Kerr black hole, and it decreases monotonically. And for, which is the red one, the SEOB NR didn't assume it. And for the NR surrogate, they have the problem that they don't have accuracy. The accuracy is up to Q8, so they don't have information in this regime. So here is our prediction. Here is totally an extrapolation because we don't have numerical relativity data here. So our model is a disaster. But we need to gain information of this regime. So we have to really think about how can we add information here, but maybe adding embryo data in this regime, which is the stream mass ratio regime, we will win also in accuracy just in the aligned spin case. Finally, about the processing case, in the processing case, both the spins are not parallel to the orbital angular momentum. So the orbital plane is not preserved. So the black holes are doing something like this, and they are described, as I said before, for a high dimensional parameter space. In fact, by 7 dimensions, 6 for the 3 of the 2 individual spins, the 3 components of the 2 individual spins, and then the mass ratio as well. And for our data set, we also add information about the spin angles, given by these formulas here. But we have a problem, so we cannot pick the information directly from the SXS catalog, because, as I said before, the frame has temporal dependence. So we need to fix a reference time in order to have all the waveforms at the same position. How can we solve this? So first of all, we get the spin evolution of each simulation. We remove the Young radiation from the NR simulations, and we compute the maximum of the total waveform amplitude, which is given with this peak. And we go 100 M before this peak. And this is going to be our reference time. So once we have this reference time, we do a co-processing rotation, which is just to compute the angular velocity and do the rotation that this angular velocity is parallel to the Z component of our frame, to the Z axis of our frame, sorry. And so we rotate it in the way that the angular velocity at this reference time is parallel to the z-axis. And finally, once we have this rotation, we also do a rotation in the co-orbital plane in order to have the x-axis defined by the distance between the two black holes. So once we have this, we can just train our network using also the neural network. In this case, because we have 10 input variables and 4 output variables, in that case, the 3 components of the final spin and the radiated energy, we built a bit more complicated deep neural network, but it's also quite accurate. So just to have a look to the comparison of results, here is much better explained. So comparing our results with the approximation used by Phenom X and SEOB, we gain 1 and 2 orders of magnitude, for example, for the final spin. In fact, a thing that is important is that we are predicting the 3 components of the final spin, and these approximations are just approximating the norm of the final spin, so we are gaining also in information. And if we compare to the NR surrogate model, we have 1 order of magnitude less than they, but one thing that has to be taken into account is that they are using 100 NR simulations more because they are using their own data. So if we add more information, we add information about the RIT catalog and also simulations from the University of the Balearic Islands, we could also gain possibly this accuracy. So just to conclude, so the increasement of the sensibility of the detectors require a constant improvement of the waveform model's accuracy, and the current models that do not cover the whole parameter space, which is a very important thing in the sense that when we are going to detect higher SNR events, the more accurate the models are going to be needed. And for the future work, so as I said before, we need to increase our data set. So we will add RIT data and numerical relativity simulations performed by our group. Also, we are going to explore more detailed stream mass ratio regime and see how it change, adding less or more points to our data set. And also, we are planning to add weights to our data set, because so we are going to join information from very different sites. So we would like to weight our data in having taken into account the amount of error of the simulation that we are using. And finally, we have to figure out how to really interpret the results of the processing case. So that's it. Thanks a lot for attending. So I'm happy to answer questions or comments or.
Thank you.
We have some time for questions and comments.
Hi, thank you so much for the talk. It was really nice. So I have many questions, to be fair, because I'm not an expert in waveform modeling myself. I only know a tiny bit of machine learning. So maybe you can help me out a bit. So in a sense, what you're trying to do is to solve equations for waveform modeling, right? Because you input some parameters and then you output some other parameters, and then the network, what it's learning is the equations to be solved.
Yeah, basically, yes.
So I'm actually very surprised that you were able to get something with only dense layers. That's very surprising, to be fair. And I don't know if it helps, but some people, probably outside our community, they are trying to do same type of problem, but in different things, like for instance, chemistry, where they try to model new molecules and so on. And they are using graph neural networks.
I see.
So those are actually quite complicated, and I know nothing myself. So I would assume that something for processing signals is, well, I don't do processing signals myself, but in my group they are very into those things. So if you want to talk about it, that's
so we can, yeah, that would be great. We can discuss it afterwards. Yeah.
So the last part is that I would assume that you would need some type of comparison with other methods, like for instance parametric estimation. So I think that will be something that will add even more value to your work for future. But so far it looks super interesting and very complicated, by the way.
Thanks a lot.
No problem.
Other questions or comments?
Thanks for that. I have nothing to add to all the modeling part. I just want to signal boost one of the advertisements you made earlier on. If you go back to slide 2, like I was explaining about these different generations of the waveform models, and saying that the D was good at the first observing one, but now there's the new ones. And I think I saw 1 or 2 talks where people were still using the Phenom D model. So anyone, you really should upgrade to this new Phenom X family we have. And if anyone has questions about, talk to me or even better to write it.
Good advertisement. I have 2 questions, if I may. There are no other questions or comments on this level or discussion. At the end, you were showing the results of different other different groups, and then they were different as far as I saw between your model, for example, the surfing pH. The difference is more or less order of magnitude, but you are showing that they are using like 10% more simulation. So does this make such a huge difference? You have 1 order of magnitude in precision or in final result, but only 10% more in training. Can you explain this?
So I'm not really sure because we haven't tried it yet. So we would like to add also more data. So I have not the proof that we are going to improve 1 order of magnitude, but in the sense that we are playing with very small number of examples of adding just more knowledge.
Adding always is good.
Yeah.
More.
Yeah, exactly.
And the second question is about this precision, because you were mentioning the possibly high signal to noise events that we will have in 04 or 5 and so on. So because at some point maybe you don't need extremely high precision, maybe you just need something. So are you kind of studying this too? Because maybe there is a limit on what we need to do. Maybe we don't need a huge precision. Maybe this is sufficient, right?
Yeah, in fact, so the problem, the real problem here is that the current models that we have do not cover the whole parameter space. So so surfing is quite accurate enough for the moment, but the issue that it has is that the NR surrogate people does not cover the whole parameter space. So when we move a bit far away from here, we have issues in the parameter estimation. So the accuracy is in the sense of this kind of accuracy in order to really cover the whole parameter.
Well, but if you select the waveform that it's well within the parameter space that you cover with a specific signal to noise that is kind of realistic for 04, let's say, and you are able to recover this as good as with this kind of true waveform, numerically simulated waveforms and so on. Basically, that was my question.
Sorry, can you? I didn't get it. Can you?
So because you are trying to perform kind of a fit to a real numerical waveform produced by some complicated methods and so on, to recover it as precisely as possible, right?
Exactly.
But there is a limit to this precision because we have noisy data, low signal to noise. Signal to noise is not infinite, right? So you don't have to do everything. You have to just enough, right?
Yeah.
So my question was about are you controlling this as well?
I mean, the thing is that for as has been seen in O3A and O3B, so it depends on how challenging is the event. The things that we have now are need to be like a bit upgrade more in that sense. So the numerical relativity calibration for very challenging events is needed. Yeah.
Thanks.
add to that from the parameter estimation perspective, I would say the jump that, for example, Mighty's model has over the 10⁻⁴, the lowest accuracies of one, that's probably like the difference that really makes a difference for O4. Then the one extra order for observed in BH, I would expect that not to be relevant. So I would say having U on 10⁻⁶ accuracy over the whole parameter space is probably already preferable to the slightly more accurate in the narrow range. But this is only the final mass and spin.
Yeah, we are. So the next steps after that, we have a very solid model for these two quantities is also to do fits for the other coefficients of the parameter space. So
the full waveform model, you can actually accumulate more of the phasing across the whole waveform than it matters a lot more than it just takes two quantities. I think this is already quite late given that the question is just later waveform models.
Thanks. And let me also add to what was said before by Marisa, that this is quite amazing that you can do that with such a relatively simple neural network. It's quite nice. Okay. Do we have other questions or comments, or maybe from remote? What is suspiciously silent? Yes. All right. So then, thank you very much for your talk.
Thanks to you.
Okay, and we move to the third talk. Yes. This is the microphone.
Yes? Yes. Okay. So I'm David, also from UAB, like Maite. I have to warn you in advance, there are 0 results in this talk. It's basically propaganda. I want to convince people that this is a cool field to work on and hopefully get some collaboration out of it. But I felt that's sort of in the spirit of results action, so I'm going with it. The topic is gravitationally lensed gravitational waves, which is still a relatively new field. And since we have a diverse audience, I'll spend half of the talk just introducing the topic and then the challenges for machine learning could help. So gravitational lensing, people with an astronomy background will know this from observations in light, where you can have all these really impressive effects when light is spined around a heavy mass that acts like an optical lens, and you get sometimes even an almost perfect ring around an object, luminous arcs, multiple images, all that sort of things. It's exceptionally productive in observing the faraway universe, cosmological parameters, and so on. Then we want to, in principle, observe the same thing in gravitational waves, because the equivalence principle tells us that the trajectories of gravitational waves from a distant source, which one is the pointer? Yeah. From a source going past the head of the detector should bend in exactly the right. Question from remote?
It was an echo.
No, just an echo.
Someone probably
yes. So there can be lens just like light. In principle, you can search for similar phenomena, but the methods and the actual phenomena are quite different, mostly because we don't have any scattering solution in gravitational waves. We can't see any of these actual deformation of images. So what we can see is just the magnification by lensing, like a burning glass, making a source appear brighter. We can still get multiple images, so we don't see their sky separation, we can see the time separation because they take different paths, different lengths, and some frequency-dependent deformation effects, which is where it gets complicated. Then there's already a quite rich literature on what sort of science you can do if you eventually detect that. Spoiler, we haven't detected it yet. You can do several new tests of fundamental physics, like how long does light or gravitational waves take around different paths in the potential if we detect both of them. You can use this when you have multiple images to do much more precise localization of black holes without a counterpart, but just using the multiple images to have more detailed parameter estimation. You can also use the time delays from cosmology, the same way as already done with gravitationally lensed images of quasars, again, basically using the time delays. And you can use microlensing by small lenses like primordial black holes, intermediate mass black holes, to do population studies of those exotic sources. Most of that has traditionally focused on the future detectors like Edge and Telescope at LISA, because lensing will always be a rare effect, a small fraction of events, so you need many and high redshift detections to really see it. But I would argue it's already an interesting topic now with the current detector network, because as we all know, it's improving rapidly, having more and more sites and higher detection rate. Here's an example plot from one of the papers that studies the lensing rate. It's a bit difficult to interpret because it's plotted in comparison to SNR, rescaled to different detector sensitivity curves. But the basic message is that the rate of lensing, this is an absolute rate, so not just fraction of lensing events, but the actual number going from 0.1, where it's very low, to somewhere that actually reaches the point where we can detect a few such events at this sensitivity, hopefully. And the interest in this sort of things has grown rapidly in the community. There's a lot of lensing papers out there, and there have been a few first studies already on 0.1, 0.2 data. Several groups did this basically on open data and found some sort of intriguing candidates, things that could be consistent with lensing, but taking into account the prior rate are more likely to just be, for example, two events that just look similar instead of a multiple image of the same thing, or slightly unusual waveforms. Information could come from lensing, could come from something else. Then there was the most recent paper last year, the first Virgo official collaboration study of lensing. This was made at a point where from O3A we now had suddenly 40 more events instead of just 10 before, so it started to become more interesting. There's also an O3B analysis, but you still have to wait for the results for that. This first study focused basically on 4 topics. The text disappeared from studying the statistics, just how many lenses do we actually expect, and for O3A that was still significantly less than 1, so it was sort of fishing in the dark, hoping for a lucky break, but not really expecting much. Then the magnification effect, that you keep basically your exact same waveform shape, just go to unexpectedly loud signals. And for example, you could imagine some of these very heavy, surprisingly heavy Newton stars, surprisingly heavy black holes. An alternative interpretation is they are just lensed from higher redshifts. Then the search for repeated events, and I said multiple images, you actually only see the time delay. The last one, the so-called the microlensing gives you images that are so shortly separated that they overlap and deform the waveform effectively. And for all those searches, no promising candidates so far, so I won't go into the details of that paper, but now I'll go on to what these actual effects are, which brings us into the direction of why is it challenging to look for them and what can machine learning do to help us with that. So first, the big topic, the multiple images, which is sort of the most exciting. What happens is that you have your gravitational lens. It's a cluster of galaxies, but it could be a single galaxy. Then you have different gravitational waves, or same for light rays, taking different paths through it. And from your observation, you see 2 images at 2 different virtual positions at our resolutions. They will actually come from the same sky position, but with the time delay. And then what the waveform looks like, if you have some frequency initial parameters, then you add your new parameters, the magnification, the time delay, and the so-called Morse phase, which is just an overall phase shift from the potential it goes through. So what happens is that your inferred luminosity distance will be biased because of that magnification if you don't take lensing into account. And the coalescence time is completely degenerate with the parameters you already infer. So basically your intrinsic parameters, the masses and spins of 2 images of the same source should be the same. You just have this overall magnification, time delay, and phase shift. And then when you have simple waveforms like the D, the old one, then this wave phase shift is also just degenerate with other parameters. But if you have full precessing iron mode waveforms, it actually deforms things a bit. I'll get back to that later. For now, we assume they're exact copies, just rescaled and shifted in time. And then the first method that was suggested for that by Harris et al. Is to identify them, do the individual parameter estimations like you always do, and just check for posterior overlap. How well do the Bayesian posterior distributions match between two candidates? And if they match very well, you say, oh, maybe this was a lensed one. The problem with that is if you have n events in your catalog, which is by now almost 100, then you have to check n times n to the n minus 1 over 2 pairs. So it basically goes quadratically with your catalog size. Maybe you can filter out the ones that are obviously one neutron star, one black hole to make it less, but in the end, with current detector sensitivity, you have a huge haste of event pairs that you need to go through. Then we want to make our problem more complicated, of course. We can actually search for more such images instead of just using the published gravitational wave catalogs, which have strong super-threshold events. You can also use this information that you expect multiple similar events to make deeper focused subthreshold searches for possible lens counterparts. So for that purpose, there are two pipelines in the LBK so far, one by Lee et al. From Caltech, I think, and one by Isaac et al. That I was involved with in Portsmouth. The idea is that you build a targeted template bank that matches, if this is, for example, the Mars 1, Mars 2 space, and there's also spins and so on, you have this complicated template bank everywhere. But for each event, you can probably not see a lot, but there's like a small red star for both of these. Then you sort of build a small template bank around that just matches the parameters, masses, and spins of this event, and then look for similar ones, but suppress the overall noise background that you normally pick up from the areas of parameter space. So you're able to dig deeper into the noise and find weak signals under the hypothesis that there should be something close to this one. And these pipelines are based on the GSD-LAL and PyCVC, which are the standard pipelines, and they've already been run on O3A data, also previously on 102. These approaches are relatively cheap because PyCVC, GSD-LAL are highly optimized, and now you just work with a handful of templates instead of the hundreds of thousands normally, but still you have to reprocess your whole data set many times over. If you have 100 events in the catalog, you do 100 such searches. And so this also gets into the same growth of cost with catalogs problem. And also these two current pipelines are not really optimal. They're just the minimal modification of these pipelines to work for this case, but you can also optimize them a lot in how template placement is done, and including these actual lensing effects of the phase shifts and so on. And at that point it gets arbitrarily complicated, and maybe some machine learning or generic approach could help in this case. So let's talk about this general problem of identifying multiple images and how machine learning can help there. The main one we have to address is this almost quadratic growth in how the number of pair candidates that you have to evaluate. And if you want to just do parameter estimation and pair comparison, you have this problem. An alternative is to pre-train some machine learning classifier on simulations of lensed and unlensed populations and discriminate between them. That would maybe even allow you to do this in low latency and enable EM follow-up to see if you also have lensed multiple GRBs or something from some direction. There's already one implementation for that. There's a paper on the archive, I'm not sure if it's published yet, which basically uses two parallel classifiers. So it takes the time frequency Q-transform maps, puts that into a dense-net CNN. I should also say I'm not actually involved with that. I'm just advertising other people's work, Royal et al. For this. So put this Q-transform into a dense-net, and then something, I'm not sure what it actually does, the XGBoost algorithm. You get a probability that two events have actually the same time frequency evolution. The other one takes the sky maps, which are already also available in low latency. So these are two data products that you don't need full parameter estimation for. You have some seconds after the event is detected. And then there's also some feature extraction from the sky maps going through the same XGBoost algorithm. And then you have two probabilities that I think, I'm not sure, they just multiply them at the end. And then they get a standard efficiency against false, they call it false positive, which is false alarm rate curve. And they compare the blue is their result compared to the posterior overlap method when you have the full PE information. And in this case, they were quite similar. They actually get better efficiency at low false alarm probability, but it's still a sort of an open question, what is actually the operating point on such a curve that you want for such an algorithm? Because it depends on whether this is supposed to be your final answer or you just do an initial candidate pre-screening. So often we want to actually go to very low false alarm probabilities, but in this case, I would argue you can go to quite high false alarm probabilities because you'll still be able to use other methods to follow it up in more detail. And yeah, there's certainly different ways one can combine this information. Maybe some classifiers takes both sets of information together, or you can go to the full time domain information. So that would certainly be the ideal thing. We saw a lot of talks where people do the time domain data and make a detection, yes, no classification. Similarly, you should be able to take two sets of time domain data and make a classification whether they're consistent with the same signal provided or not. So that would certainly be more powerful than this approach. Then this one is still somewhat limited in robustness across parameter space, especially it has problems with low mass, with long duration signals, which we always know is challenging. The ideal performance, as I just said, where exactly do you want to actually tune this thing is still a bit of an open question. And then to actually make this ready for low latency. Then for these subspecial searches that I mentioned before, there's lots of improvements that could be done. One way that's already been explored in the standard CDC searches is to augment these matched filtering searches with machine learning classifiers. So that's a ranking statistic. The standard match filtering is only optimal Gaussian noise. So when you have glitches and everything, in CDC and GST-LAL, they already put in several types of machine learning using EQ information and so on to optimize it, but there's no specialized way to do that for lensing yet, where you could actually train over this parameter space of what the lensing could do to the waveform. And you could also imagine a pure ML pipeline where you take the inputs, the parameter samples of a certain event, you just draw simulations from that, train on that to have a targeted search that's really looking for copies of this in the data set then. Then let's move on. Assume you have identified interesting candidates, but you now want to really verify do they match very well or not. That's what we call the joint parameter estimation. So again, assume that they're more or less the same waveforms, but you have to include this full information, including these possible phase shifts. Then the idea is standard idea so far. Okay. So the joint Bayesian parameter estimation where you have two data sets, do a joint likelihood that combines the parameters that should be the same between the events and the parameters that should be different, and do your inference among that. And then you also need the individual parameter estimation runs with identical settings to make sense to be able to compute a base factor between the two and really have the hypothesis test of whether they are more consistent with the same source or more consistent with dependent sources. There are several pipelines so far. The ones that have been used in that OSVA analysis are inference-based one and a Bilby-based one that they differ in all sorts of things. For example, which of these Phenom waveforms they use, which is not just academic, but makes a big difference because, as I said, once you have these presetting higher modes, then you actually need to include a different phase factor in each mode, and then they overlap differently and give you actual physical deformations on the waveform. But the main point, besides all the technical aspects, that this is computationally very expensive. So already basic parameter estimation on a single event takes time, and if you have two types of data and three more pre-parameters, it gets really complicated. And especially these Hanabi ones can take many weeks on a single pair. So there has been great progress with faster methods. That's one paper by Jankart et al. The pipeline is called Golem. And also to prepare the Hanabi, there's a much faster version now, so it's not published yet. So these things can be optimized various ways, but still it's always a very computationally expensive bottleneck. So add from that waveform deformations, like I just said, this Morse phase that comes in with a 2-2 mode only is degenerate, but in the higher order mode you get deformation. Here also have the references for that. And these pipelines in principle can take care of it, but it just makes it again more costly. And then when it gets really more complicated and you can't just have that simple equation anymore, is when you have not just the single lens, but like here you have the individual galaxies and then the overall cluster profile, or you have one galaxy but was enough substructure in it that you need to take care of that. EM lensing people know all about that, and for us it will also become relevant at some point when we have the sufficient precision. Plus, then there's the case of microlensing that I only briefly mentioned before. So that's the point when your lens size, basically the Einstein radius of it, is comparable to the gravitational wavelength. This is basically a case electromagnetic observation never happens, but because gravitational waves that we can get with LIGO are relatively long wavelengths, this can actually happen. And then you don't have geometric optics anymore, you have frequency-dependent amplification. The phenomenological way to think about it is what I mentioned before, that you have beating patterns where you have all the different paths close to that lens that overlap, and you can't actually have time resolution and they interfere with each other. And basically it gives you, when this is the unlensed waveform, some sort of additional up and downs, which actually looks kind of similar to what precession and eccentricity can do. So you also have that degeneracy with complex waveform models, so it gets really messy. And it depends in detail on the density profile of the lens. So first searches always use a point mass approximation, which will be okay for a black hole, but not for anything more complex. So there will be complication from that. And also, again, when you have that embedded in a larger structure, then you also actually need to do microlensing and storm lensing at the same time, which people are only just starting to have methods that can deal with that. So for these two cases, microlensing or strong lensing or even combination, what are the challenges in parameter estimation? With speed, you need to be faster than what we currently have to deal with the big catalogs and be flexible enough to take into account realistic lens rules. So that we can help with these two things using machine learning, like we heard Joe's talk, the weather parameter estimation talk already. So there's two approaches. One would be that you just augment your classical Bayesian parameter estimation with machine learning. So there's a few cool tools that I'm aware that already exist. NESA from Williams et al. And will be MCMC from Ashton et al., which use traditional method sampling or MCMC methods respectively, and just augment them, making the proposals or some other steps much faster with machine learning. So that can certainly help, but they've not been characterized for the lensing case yet, where again you have more data and more free parameters that you need to look at than standard CBC parameter estimation. And at least build the MCMC, I've tested this with a colleague, and just in standard configuration, it doesn't work at all. You need to somehow adapt the proposal distributions to work in the higher dimensionality. And that's basically the challenge here. Then there would be the possibility to go to pure machine learning, where you directly emulate the posterior. The autoencoder thing looks promising. There's this thing called simulation-based inference and other approaches where you completely bypass the traditional samplers. There's one paper that explores this for the microlensing case. And I think I just added that point at the end. Vitamin sounds really promising for this thing, but you have to retrain it on this dimensional parameter space, but could probably work. Let's see. And then another point, the lens modeling itself, which has been very little explored so far on the gravitational wave side, but there's a huge experience on that in the electromagnetic world already. And actually machine learning is already a huge thing in electromagnetic lensing because they basically have much larger data sets. So we talk about the big catalogs, but hundreds of events is completely negligible to the 10 to the 5, 10 to the 6, whatever galaxies they have in modern surveys. And so they do, for example, there was a gravitational lensing data challenge recently, which some people won with a machine learning quantifier. And there's a really impressive paper they have for that. So this is a question of how you find things, and there's some of these things we can learn from them. So again, the data analysis problem is very, very difficult because they have this rich geometric data, and we just have time series. But then there's one thing that can translate, which is the modeling of the lenses, which in their case, again, they have more information, but also for us, it helps in actually translating what the parameter deformation should be. And there's also papers galore already that use machine learning to model that, because you have some family of traditional density profiles Cersei profile, Diagonal profile, and so on for galaxies and galaxy clusters, but they're all just models, and the reality we know is messy. Galaxy clusters and galaxies have lots of substructures, so there's a rich field of people who do the advanced modeling using deep learning from structure formation simulations, for example. So just to wrap up with the future outlook of, again, repeating why should people care, why is this interesting? At the current detector network, we already have chances of detecting something. And then beyond the Einstein telescope, Cosmic Explorer, and LISA, this is absolutely expected to become a regular thing. From all we know from the electromagnetic world, the lensing rates, it has to translate directly because gravitational waves follow the same trajectories. And we know there will be many of these. You have the deep cosmological reach, so all the signals also have plenty of time to pass by interesting lensing. So this will happen, and it will allow us all these new cosmological applications. And we hope that machine learning can help us make that a reality. So questions and suggestions, hopefully.
Questions and comments.
Thank you. Very nice talk. If you could say a bit more about computational complexity of the method, where is the exact problem?
So, for example, there are different problems in it. So one is the identification of the candidates for the multiple images. So basically, our current catalog is. Oh, how did I do that? So we're currently standing at this total of 90 official detections, plus maybe a dozen more from other groups, and then you already have 10,000 possible candidate pairs that you have to look for. In 04, it will be another order of magnitude higher, and you just takes too much time to go through all of them. So you need, at the very minimum, a quick classifier to discard the obvious non-candidates, so that you're then able to focus your expensive follow-up, the joint parameter on candidates. And then on that one, you basically go from your original gravitational wave parameters, which are here included just that one little letter theta, which is the mass, the spins, distance, all the angles, and so on, which typically is, I think, 11 parameters. And then you add these 3 parameters of magnification, time, delay, Morse phase, even if you are in a completely geometric limit. And when you're in the phase where microlensing happens, then you also have to explicitly model the impact parameter of how far from the lens you are, and the lens mass goes in as a specific parameter in the point mass model. Then in more complicated profiles, you get more parameters, so you are at 40 up to maybe 20 parameter spaces.
You reduce somehow the number of parameters.
So you can, if you go to complex models, complex density profiles, probably in most cases you don't need to actually add all the physical parameters. You can do some effective parameterization, similar to the effective spin parameterization that might have mentioned for the gravitational wave sector, but it's not very well explored. And in any case, basically every parameter dimension you add makes your standard Bayesian approach more complicated. It's not really a high dimensionality compared to some of the really cool methods that are out there in the literature. So in some fields, they routinely do Bayesian parameter estimation for thousands of parameters, but none of that is demonstrated to really work for relatively low signal-to-noise ratio problems in gravitational waves. So I think we're really pushing a limit where it's possible if you have enough supercomputer time to throw at it, but it would be really things like vitamin just look like much more promising approaches to that. Maybe that you can still use a traditional sampler on just the very small handful of final candidates that you want to publish to make sure you really trust it.
So it seems that you should wait for quantum computer to resolve all the problems.
I'm not sure if there's any proof that they will be more efficient at parameter estimation specifically.
I think vitamin that seems to be a rather better choice at least for now, when we don't have quantum computers, something like that. Other yes.
I think I missed the part. Did you mention there is some degeneracy possibly with the processing case?
Yes, so specifically the microlensing. So at the very first phenomenological level, it's you add additional oscillation periods in it, which is what precessing does and which is what eccentricity does. In detail, they will look somewhat different, but we have limited SNR, limited resolution still. So this is a part where there's certainly some degeneracy. I am not aware of any work yet that has really quantified how bad that is, because you need a proper model, including all the effects to start with. And the analysis that went into this 03A paper, here there's some of these base factors and posteriors of the lens mask from that. They already used the XPHM, so at least the degeneracy with precession in principle is included. And they actually found that when you on, I don't remember if it was phenom D or phenom X, but the aligned spin one with microlensing, then they got a few cases with relatively high base factors, saying it prefers the waveform with the added complexity. But then when they went to XPHM, which now has the complexity also in the unlensed sector, then the base factors went down across the board. There is actual degeneracy that it can fit if you don't account for it. And then eccentricity is the next one that no one has ever tested.
Okay, thank you.
I have a question, a simple question about this catalog with n events. Do you really have to do the n times n minus 1 over 2? Because some of them are completely different sky positions. So maybe you can.
Yes, so that's why I'm saying having some simple pre-classifier like this one that really only uses the low latency available data can make your life a lot easier. But on the other hand, we know that sky positions are tending to shift at least somewhat with the full parameter estimation, so you can't be too strict at this case, which is why I was arguing I'd like really to see something that's optimized for relatively high false alarm probabilities, which is not the usual working point.
Yeah.
Because it's fine if you pass on twice as many as real things, as long as you still have some further filters down the road.
Okay, thanks. Other comments or questions, or remote comments or questions? No. Okay, so if not, then thank you very much for this very inspiring talk. Thank you for all the talks of this session. All were very nice and very diverse. I very much like this. And we went through many topics today. And I give the microphone to Iza. Yeah, we have now a time for coffee break, so we will take half an hour and come back at 11:45 to 12. See you then.